Hello everyone, I'm Lei Zhang from Google, and I work on SPIR-V tooling in Google. In the past year, we have been working very actively to enable common HLSL patterns to be used in Vulkan. It has been quite successful thus far, so it's a great pleasure for me to be standing here to share the exciting advances in jitter toolchain for HLSL targeting Vulkan. I will firstly talk about what projects are involved in jitter toolchain, and then give you updates what features are recently covered in both the HLSL and the Vulkan side. Then I'll give you some highlights on common controls of using DXC. So before diving into the details, I'd like to look back and talk about history a little bit. Translating HLSL into SPIR-V for Vulkan consumption is actually pioneered by Lei. That was 6 months ago, before actually Microsoft open sourced their next generation HLSL compiler DXC. And we thought that it's a great opportunity for us to share the front-end parsing and HLSL verification also evolve in sync with the language, since HLSL is known as language without a spec, that the compiler defines what is acceptable HLSL. So we started contributing a SPIR-V code gene, also known as SPIR-V, that's the code name, since last April. And we learned a lot from Lei's experience. And we still cooperate with Lei if features learned in both compilers to keep a consistent experience for developers. Fast forward to today, DXC has already outgrown Lei. It supports more features than Lei and more sophisticated code patterns. So as the forward path, we recommend you to use DXC. And this talk will be also focused on DXC. Now let's dive into technical details for jitter toolchain. We want to provide a one-stop experience for your HLSL compilation. So you just need to invoke one command, that's it. But behind the scenes, there are multiple stages going on actually. Given an HLSL source, the compiler needs to first do front-end parsing to translate it into unstructured abstract syntax tree. Then initial code gene translate that AST into what is called vanilla SPIR-V here. Vanilla SPIR-V is not immediately consumable by Vulkan. It must go through a stage called legalization, which I will explain more later, to make it legal SPIR-V for Vulkan consumption. Then we just run a bunch of GPU agnostic optimizations to make the jitter performant. Verification is the last stage before the compiler actually output the final SPIR-V. It helps us to catch any compiler internal bugs. If there is something wrong that fails verification, you'll see an error message showing compiler internal error generated SPIR-V is invalid. Then it is time to submit a bug report. So all these stages are internal to DXC. Normally, you don't need to worry about them and just leave it to us and trust us. Legalization is basically, legalization is run if necessary. Optimization and verification are always on by default. The initial code gene is in DXC's code base. Legalization, optimization, and verification is outsourced to SPIR-V tools. Besides about 2 projects, there is another project you may want, that is SPIR-V-Reflect. Especially reflection is part of your workflow. I'll also talk about this project. So about legalization. As said before, legalization is a must for certain HLSL workloads. This is because HLSL is a fairly permissive and flexible language. You can be very creative when writing your source code, like grouping resources into structs or structs, passing those structs into various functions, and then use getter functions to retrieve struct fields when actually doing operation on the resources. Basically, all those kind of C++ object-oriented-ish stuff. And these code patterns, if you translate it literally, it will generate SPIR-V that is illegal for Vulkan consumption. Previously, HLSL can only be compiled by FXC. So FXC is a highly optimizing compiler. So drivers are expecting HLSL-derived artifacts to have FXC equivalent transformations done. That means we need transformations to legalize the SPIR-V to make it much simpler and more streamlined, like DXPC generated from FXC. These transformations are nothing special than normal compiler optimization transformations. So they share the same infrastructure as optimization within SPIR-V tools. This is an entirely new area for Vulkan. We have been largely addressing legalization issues in recent months, and it has been quite successful thus far. We have covered all the cases that we are aware of, but certainly we may miss something. So if you found one, please don't hesitate to fire issue towards us. I'll give 2 examples to make legalization a little bit easier to understand. So in this simple code, we have grouped a texture and a sampler into a struct, and then we pass the struct into a function and do sample inside the function. This code, if you translate it literally, is not accepted by the drivers. It is illegal SPIR-V for Vulkan because both textures and samplers are translated into opaque types in SPIR-V. Vulkan does not allow writing to opaque type right now, at least. So we must apply standard compiler optimization transformations to remove the struct and also the function call and do the operation directly on the global resources. Then the driver is happy. A similar example here, we are passing a append structured buffer around. Note that this is not copy. This is actually creating aliases out of the original buffer. And it's like passing pointers around. And this code is also, if you literally translate it, is not accepted by the driver. We need to apply transformations to remove the function call and also local aliases. That's about legalization. Regarding progress and the current status, we have been working very actively in both DXC and SPIR-V tools. We are the number 1, number 3 contributors in DXC, which is Microsoft's repository. The varied GitHub username anti-against is me. And we roughly have 1 pull request landed per day on SPIR-V tool side. So we care about your feedback very much. And normally if it is bug that does not involve the spec or the driver, we can get it fixed within 2 days in DXC and roughly within 4 days on SPIR-V tool side. So we consider the whole shader toolchain as mature-ish. So yeah, encourage to give it a try and let us know your feedback. So on to feature coverage. On the HLSL shader model side, we have fully covered shader model 5.1 and below, except those features that are not translatable into Vulkan. 6.0 introduces wave intrinsics, or also known as wave-ops, and also 64-bit integers. We have already fully covered that. And 6.1 introduces 2 system values, view ID and barycentrics. View ID is translated into an extension, KHR multi-view, and barycentrics is right now translated into an AMD extension. If there is because there is no KHR EXT extension existing right now. If there is one up in the future, we'll switch to use the KHR or EXT extension. We are currently working on 6.2 16-bit types support right now. And on language features side, we have covered CH features a long time ago. Recently, DXC has much better C++ features coverage. Resources types and their associated methods are all covered, unless not translatable to Vulkan. Namespaces is supported. This includes various symbol resolution cases. that do you know that you can actually have a global variable inside a nested namespaces that you still need to collect that global variable into the global C buffer? It is actually not that trivial to support namespaces, but we have it supported. We have also better object-oriented feature coverage right now. We covered class members, class methods, static versus non-static, this pointer, etc. And inheritance is now also supported, including casting from base type to derived type, from derived type to base type, or whatever. And common code patterns developers would like to use is like grouping resources in structs and aliasing structured buffers. Basically, legalization is trying to solve. Of course, well supported. Bringing HLSL into Vulkan is just half of the story. We also want to let you to able to utilize Vulkan features inside HLSL. So if the feature is directly expressible in native HLSL, that's great. But sometimes concepts are Vulkan specific. To express those Vulkan specific features, we need new language constructs. The general philosophy is to be less intrusive, so you can return the portability of the shaders as much as possible. So we normally resort to C++ 11 attribute syntax a lot, and we only add native types, built-in types or methods if truly necessary. The C++ 11 attribute syntax still breaks portability right now because we are still basically relying on FXC on the DirectX side. And FXC doesn't support this syntax, but things will be much better once DXC gains its ground on the DirectX side. These attributes will just then be warnings, so you don't need those ugly if-def anymore then. So we have wiki bonding and wiki counter bonding for assigning descriptors to resources. And also you can attach wiki push constant to a struct variable to make it a push constant. And we introduced two built-in types for subpass inputs. I will not go into details about push constant subpass inputs here. You can learn these concepts in the Vulkan spec. They are Vulkan specific. And we have a unified way to express Vulkan specific built-ins is using wiki built-in. I have example showing device index to follow. So for extensions, we have supported a bunch of extensions thus far, and I'm not going to read them one by one. So we are in the progress right now supporting 16-bit storage. Direct descriptor indexing, which is Hai is going to talk about, is actually landed just today. So hopefully I talked enough to spark your interest in using DXC. Here's where you can get it and its documentation. We heard you that you don't want to build the compiler by yourself, so we paid Appleware and set it up. So you can now download the pre-built binaries for release build from Appleware by following the first link. And if you still want to go hack it, you can still build it by yourself by following the second link. And we keep a very extensive documentation of how we actually translate HLSL Vulkan features, and we couple tightly that doc update with Toolchain. So you are encouraged to take a read of the manual to learn all the details. I'm also in the process of writing a series of blog posts to explain in detail selected topics. Hopefully you don't need to actually worry about the generated SPIR-V, but sometimes things just go wrong. You need to debug SPIR-V. You may find some weird looking SPIR-V patterns. We may have a reason for that. Hopefully this blog post can give you understanding of the difficulty of translation and explain why we do certain thing in a certain way. Yeah, and so you can debug better. So on to tips of using DXC. The first thing I'd like to talk about is how you can actually control target environment and extensions. By default, the compiler is targeting Vulkan 1.0. You need to specify -f SPV target in to change that. And by default, the compiler just selects whatever suitable extension for your input HLSL, because I think you give me the HLSL you surely want it to be compiled. Just no need to indicate I need this extension anymore. But sometimes if you want to manually control what extensions can be used, you can use -f SPV extension to whitelist allowed extensions. Example of using target environment. In this simple code, we are using wave-get lane index, which is translated into Vulkan 1.1 subgroup ops, as Daniel said previously. So if you are using the default settings, the compiler will show you a clear error message showing that this is a Vulkan 1.1 features, but it is not permitted to use. If you specify -SPV target in, then the compiler is happy. Basically, just trying to let it explicit. And for extension, we have this pixel header, which takes 2 input variables that requires 2 extensions. This is also how you can use the wiki built-in for specifier built-in. If you are just using the default settings, the compiler just go ahead and emit SPIR-V that requires both extensions, device group, and multi-view. But if you only whitelist one of them, the compiler will error out showing that the other is needed for the other feature. And you can use ktar as a special value here to whitelist all ktar extensions, because ktar extensions are just special, maybe. And the second and the third thing I'm going to talk about is all about resource management in DXC, because resource management is likely to be the majority of your work when porting stuff from DirectX to Vulkan. So we are trying our best to provide multiple control methods so that you can choose from to satisfy your needs. This one is about assigning resource descriptor. You can use wiki bounding and wiki counter bounding to specify in the source code. This is the most explicitly control. It overrules the others, or you can reuse register annotations. But one thing to notice is that register annotation has 3 levels of control. It has space, register type, and register number. But we only got 2 in Vulkan. It is set number and bounding number. So register type is ignored. That means sometimes we may map multiple resources into the same descriptor. Then you'll need the command line option to shift the bounding to make them not overlap. So example to show this, we have 5 resources here, 2 samplers, 2 textures, and 1 UAV. On the command line, we set to shift all samplers in set 1 by amount 10. So sampler 1, which is in descriptor set 0, is not affected. It's still taking bounding number 1. But sampler 2 in descriptor set number 1 is affected. It's taking bounding number 11 now, shift by amount 10. Similarly for the textures, they are all affected by the command line shift because we are specifying all as the value means effective for all sets. So 2 textures are all taking 52 instead of 2. For the UAV, although we specify a shift amount, it is ignored because wiki attribute takes precedence. And so we are still seeing the main buffer in bounding 100 and the counter buffer for the main buffer is in bounding number 200. The one other thing that you may want to pay attention to is the resource layout. There are subtle differences between the layout roles of Vulkan, DirectX, and OpenGL. It can easily cause you long debug time. So we actually, to support that, we actually support 3 set of layout roles. The default is Vulkan. You can refer to the doc you can refer to the doc to learn what I mean by vector relaxed here. I won't go into details. And also DirectX layout roles, which can be turned on by -fvk use dx layout. Note that this is not officially supported by Vulkan yet, or extensions. It just happens to work, and I think it helps the porting sometimes. So if you still want standard 140, standard 430 strict, you can get that by using -fvk use DL layout. We also support pack offset upon community request, so don't be shy to send your feature request to us. In the toolchain, another tool that you may want is SPIRV-Reflect. It is a small C++ library that developed by Code and High. It contains only one header and one source. By using this tool, you can reflect lots of information from the SPIR-V very easily, like vertex attributes, distributor bounding sets, and so on. Also information. Ask Kai about this awesome tool. He's going to talk about, although not this tool, in a minute. So by no means DX is a small effort. I must thank everyone behind this to make it happen. Here's a list of individuals and companies and group. Apologies if I miss anyone. Outreach to the community and also the IHVs has been very valuable for us. So please give it a try and share your feedback with us. That's all I have for today. Thank you. I'm happy to take your questions.